Hello, I'm Alexander and I will be presenting an article called Staged Integration of Recurrent Soft Actor-Critic for Bioreactor Control as a part of Smart Industry Conference. And before we proceed to the main part, let's talk a bit about bioreactor as a concept in general. A bioreactor is a device that creates a controlled environment in which a certain bioprocess can be conducted, and bioreactors are widely used in many industrial areas, for example for creating vaccines, biofuels, growing tissues and organs, treating wastewater and so on. And obviously the more advanced bioprocess gets, the harder it is to control a bioreactor in an optimal manner to support this environment. And here are the main challenges associated with autonomous bioreactor control, namely its high complexity and stochastic nature of bioprocesses, limited measurability of the system because there are many parameters that are impossible to measure directly or impossible to measure in principle. Also, exploration of such environment is always expensive because a biomass is required, a substrate is required, a lot of supplementary material is required, and it usually takes long hours to observe the results. And this in some makes creating accurate mechanistic models of bioprocesses a really challenging task, and there is always some kind of model reality mismatch. And the problem is that a lot of popular autonomous control methods, for example model predictive control, they are limited by the quality of the model they use. So for example, if some byproduct accumulates over time in a bioreactor, then the system's dynamic would change critically, and even though the model worked once, it would not be applicable anymore. So in terms of bioreactor control, we need some kind of adaptive control mechanism that would be able to adjust the policy on the fly based on what is happening in the environment. And recently there is a steadily growing scientific interest in reinforcement learning methods in the context of bioreactor control. And reinforcement learning has even been shown to be able to address most of these issues. However, such problems as expensive exploration and limited measurability remain critical. And this study aimed to tackle these challenges by synthesizing a hybrid approach that would combine memory-based reinforcement learning to tackle the partial observability of the system and offline to online learning to decrease the need in exploration steps which are expensive. And in short, memory-based reinforcement learning aims at giving the agent a memory module, usually it's a sequence network, a recurrent network or transformer, using which it can approximate the current system's latent state by utilizing the history of observations it received during the interaction with environment. And we've chosen to use recurrent soft actor-critic with LSTM layers as the agent because of many advantages that soft actor-critic has. Speaking of offline to online, it's a pretty straightforward idea. So after the agent is created and before it is integrated into the environment, there is an intermediary step where this agent is augmented with some prior knowledge about this system, and it can be in form of just plain data, but as we are training model-based reinforcement learning agent, which requires sequences, we have chosen to go the approximate simulation way. So based on the gathered data, simulations are reconstructed, for example, via system identification methods that are used to pre-train the agent. And after pre-training, when the agent is integrated into the real system, it kind of knows in general what to do. So it converges faster, it needs less exploration steps, and even when the agent explores environment, those exploration steps are less risky because it's already familiar with the state space of the system. In order to approbate our approach, a custom environment was created based on Baker yeast bioreactor model proposed by Pandian and Noel in 2018. It was modified to be stochastic and partially observable, and there were 3 simulations used, one true with observation noises that represented the real system, and 2 deterministic approximate simulations with slightly changed parameters so that they are not the same to the target system. They are quite different, but they still represent those laws that underpin the system's dynamics. And here you can see the results of applying our approach. Here, the memory-based reinforcement learning agent with pre-training is compared to memory-based reinforcement learning without pre-training, because pure reinforcement learning is unapplicable to partially observable systems. And as you can see, indeed our approach allowed the agent to converge way faster. So we can see that each time step is 1 hour in the context of our simulation, and we can see that the agent, pre-trained agent, converged to good policy approximately about after 6 hours of inference, and it took 14 hours for the agent without pre-training to do the same. And the agent with pre-training also scored lower scores on error metrics, and yes, this proves that our approach is indeed functional, and it may be helpful to optimize the process of integration of reinforcement learning based controllers and make all of this less risky from the economic, financial, and manufacturing perspective. And further research lies in exploring non-stationary environments with growth inhibitors that prevent, after accumulated, they prevent cells from multiplying further. Also, there is a need in hybrid control methods that would be deterministic in order to minimize risks, because even if we are sure that the agent, any reinforcement learning agent, would most probably not make bad decisions, we cannot guarantee that it would not happen in principle. So we need some kind of mixed hybrid architecture that would prevent stochastic outliers from affecting the overall performance and affecting the quality of the valuable product. And there is also a need in pre-training regularization techniques when in the context of approximate simulation pre-training. Because, for example, we can see that rollout of policy obtained at 5th episode showed that pre-trained agent has a slightly less accurate control, and this is because it was hindered by the previous experience. So he learned the approximate model too well, and he was confident that like it works the way it needs to work, and yes, this issue should also be considered in future. So thank you. Do you have any questions?